Our lesson for today will be looking at Chemistry 1502. The topic for today will be looking at isomers, but we will be looking specifically at stereoisomers, and then the subtopic is conformational isomers. This is lesson 101 under stereoisomers. Let us start. If you can review, we do have lessons based on isomers, but a different type of isomer, which is constitutional isomer or structural isomers. Just know that we are talking about one the same thing. So today we'll be looking at the lesson series of stereoisomers. Sometimes it is also known as spatial isomer. So instead of seeing the word stereoisomers, you will see spatial isomers. Just know that we are talking about one the same thing. And then under spatial isomers, we do have different types of isomers, the same as structural isomers. We know that under structural isomers, we do have chain isomers, we do have functional isomers, positional isomers. So also in stereoisomers, we do have different types of isomers, which we have distereomers. It's actually distereomers or diastereomers, and then we have enantiomers, which these two are different. And then under diastereomers we have geometrical or geometric isomers, and then we have conformational isomers. So this is the three under spatial isomers. Just know that under spatial isomers we have two different types of isomers, which is diastereomers and enantiomers. If you can check one of the lesson series, we do explain enantiomers together with chirality of a carbon or a certain structure. So today we'll be looking at the diastereomers. Under the diastereomers we'll be looking at conformational isomers. So that is today's topic. But before we do that, we have to review what is a structural isomer. Once we understand this, it will be simple for us to understand the spatial isomer. So a quick review. If you remember very well, when we talk about a structural isomer, we are talking about different compounds with the same molecular formula but different connectivity or different structure. So the molecular formula might be the same, but looking at the structures, you'll find that they're not the same. So that is a constitutional isomer. So for example, let us look at the C2H6O. We do have two carbons, 6 hydrogen atoms, and 1 oxygen atom. We can draw this in this manner. Is hydrogen atoms, and then we can put our lone pairs here. It's fine. So looking at this, we can see that we have represented this molecular formula using this structure, but we can also use another method or structure to represent this. We have two carbon atoms with 6 hydrogen atoms and an oxygen. So you can see both of the structures, they represent this molecular formula, but they're different. So the connectivity of structure A and structure B is not the same, but the molecular formula is the same. That is the structural isomer. So you can clearly see that the connectivity is not the same. This is a dimethyl ether, and then this one is methanol. It's actually ethanol. So you can see that they are not the same when it comes to connectivity, but the molecular formula is the same. Just to quickly review again, let us try to draw the isomers for this. We have 1, 2, 3, 4. It's butane. It has 4 carbon atoms. Then we put our hydrogens here. We have 10 hydrogen atoms. So this is butane, or we can say it's an butane. And then looking at another structure that represents this molecular formula, we have isobutane. Can quickly fill in these hydrogen atoms. Then this one also has 3 hydrogen atoms. If you can check, we do have 10 hydrogen atoms. It's isobutane. So you can see that the molecular formula is the same, but the connectivity is not the same. With that being said, let us go to our topic for today, which is stereoisomers, or spatial isomers. Now, what you have to know about spatial isomers is that we have different compounds that have the same molecular formula and the same connectivity. So you can see the difference. The molecular formula is the same, and also the connectivity is the same. But the difference is that the arrangement or the orientation in space is different. So in 3D view, you will see the difference. Now let us look at the conformational isomer. Remember, I said this is under the stereoisomer, whereby the connectivity is the same and also the molecular formula is the same. Now, when you talk about a conformational isomer, in order to understand this, you have to go through the Newman projection topic in order to understand this particular topic. Because in order to get a conformational isomer, the only thing we can do, we can convert from one isomer to other isomers by just rotating about carbon-carbon bonds. So let us quickly look at an example. Let's say we have ethane. Remember, in this conformational, in this isomer which is conformational, we have to represent at least the 3 dimension. So we know that we have 2 carbons and 6 hydrogen atoms. So let's say we represent it using this manner. If we rotate this direction, we are going to yield a structure like this. I'm trying to make sense out of these drawings. I hope it makes sense. So you can see that if we rotate, this part will actually go this direction and will yield this. So the two are actually isomers, specifically conformational isomers. We know that from the Newman projection, this is a staggered conform, and then this will be eclipsed, totally eclipsed conform. So the two are conformational isomers. We can use another method, the method of which we are familiar with. Looking at this view, and then behind we have so rotating this to yield another structure, we are actually yielding another conformational isomer. Remember that we can rotate this direction. We are going to yield another isomer, which is a conformational isomer. So I hope you do understand what is a conformational isomer. Just a quick summary: conformational isomers are stereoisomers that can be converted from one isomer to other isomers by rotation about carbon and carbon bond, and this is mainly based on the Newman projection. In the next lesson video, we'll be looking at more stereoisomers. That's it for this lesson. This is Paula SJ. Thank you very much.